Hi friends, so today I'm back with another beautiful problem on binary search tree. So the question is, we are given a binary tree, we have to check whether this is a BST or not. Okay, so you can think of one idea at least. At least let's just discuss the idea one. So the first idea is simple. We know the in order of a BST is sorted. So first thing is we can do the in order of this binary tree, and if this in order comes out to be sorted, then we can say it's a BST, otherwise not. So first is check if in order is sorted or not, which will require time complexity of order of n. And because you're going to traverse over the whole tree obviously, and space complexity is order of h for the recursive stack space and n for storing the in order. So this is for recursive stack space and n for storing the in order. Now can we do it any other way? Can we do it in, maybe can we save this order of n space? So there are many ideas, so I'll discuss one beautiful idea just I want to share with all of you. So the idea two, so it's a very unique and different kind of idea, that's why. So if I ask you about root of a BST, can you tell me what value can the root have? What can we have in the root? So we can have anything in the root, right? I mean, the range of this root element is minus infinity to plus infinity. It could have been any element in the world, just this root element. If I say guess a BST, you can guess any possible root, right? There is no limit to that. Okay, fantastic. Now, if I come to the left of it, if I come to this node, whatever this node is, I don't know what is this node. What can be its range? Since this node is 10, 100% left subtree is smaller than that. So this node can be at max 9, correct? Because it has to be less than 10. Minimum it can be up to minus infinity. So the range of this element becomes minus infinity to 9. While on the other hand, the range of this element, since this element is 10, I don't even know what this element is, but 100% this will be greater than 10. So it will be 11 to infinity. Hope it makes sense. Now, let's come to this element. Now, what can this element be? Let's forget there is a 3 here. What can this element be? So whatever it is, it has to be less than 5, correct? Because, in a BST, left subtree is smaller than the root value. So 100% this is going to be, minimum it can be anything, but it can be at max up to 4. Why? Let's come to this. So since this root can be maximum up to 9, okay, how do I know it can be maximum up to 9? Because this is left of this 10, so 100% this whole subtree has to be smaller than that. So this whole subtree's range, this range is not for this only this element, this whole subtree's range, but specifically we are defining for this one. So this element has to be greater than 5, and at max it can be 9, right? It can be anything from 5 to 9. Oh sorry, 6 to 9, because 5 is already this element, so it has to be greater than this, so 6 to 9. Now coming to this element, it has to be smaller than this 9. Minimum it can be 6, so maximum it can be 6 to 8, right? Because this one is already 9, so this side has to be smaller than this one. Make sense? Now coming to this one, this element 100% has to be smaller than this 15, so maximum it can be 14, minimum it can be 11. Okay, because if it goes below 11, then it will violate this particular node, because everything to the right of because we have a 10 at root, everything on the right subtree has to be greater than 10. So I can see it here. I'm getting these values from my parent, but I'm just showing you from the root level. So just because this range was 11 to infinity, this guy minimum value will be same, but maximum it can go up to whatever this value is minus 1. Now let's guess about this one. This has to be greater than 15 at least, because it's in the right, but maximum it can be whatever is the maximum of parent, infinity. Now let's come to this 9. This has to be less than 20, so at max it can be 19, but minimum it can be what? Minimum it can be 16 from the parent. It could have been anything from 16 to 19, and that is fine. Now coming to this node, this can be what? This has to be greater than 13. So at minimum it can be 14, and at max also I'm taking it from the parent, it can be 14 only. So there was no other option for this node. Now this range I will keep on passing to every node, and whichever node first violates it, I mean if any node violates it, we know it's not a BST. For example, this node was supposed to be in between 16 to 19, but it's 9, so it means 100% this is not a BST because of this node. Hope it makes sense. So let's just write this function. Bool is BST, and I'm given the root node and the range of this one. When initially we call this function with the root guy, start and end would be what? This will be, I mean the smaller value could be minus infinity, which is in our case int dot minimum, and end could be int dot maximum. Hello, hi everyone, how are you? Today we are going to do a very beautiful question called delete a node in binary search tree. So it looks simple, but there are some edge cases in which it gets problematic. So let's just see. The question is pretty simple. You are given a particular k value. Let's just say k equal to 30, and you have to delete this node out of BST. So this looks highly similar to insertion, but there are some edge cases. So I'll explain you all the edge cases one by one. So let's first discuss on trying to delete k equal to 5. If I want to delete k equal to 5, it means this node. So what I have to do? I have to do its parent dot left, since 5 is left child, equal to null, right? I'll first go to reach to this 5. How will I reach? I am at 35. I know it's a BST, so left nodes are smaller, left subtree is smaller, right subtree is larger. Since 5 is smaller, it will be 100% on the left side. Then I reach 20. Again, I'm looking for 5, which is smaller, so it will be on the left side. I reach 10. I'm looking for 5, which is smaller, so 100% it will be on the left side. So I have to delete k equal to 5. Correct? So first thing is searching for the element. So for searching, I have already written down the boilerplate code. Now, first I have to delete this k value. I'm given the root node. I'm simply saying if root data, if I am 15 and you are looking to delete 10, I have to do the deletion from the left hand side. So I'm saying, hey tree, hey binary search tree, hey my left subtree, I'm making call to the left, delete 10, or maybe let's put it this way. Let's just say I am 15 and you want to do deletion of 10. So root dot data is greater than 10, 100%. So the data is on the left hand side. So I'm saying, hey left subtree, delete 10 out of yourself wherever it is, and then after deletion, whatever is the root of BST, just return me that. I'll make it my left child. Okay, this is how I'm doing the call. This is what my faith is out of recursion. Now this is the other case. The other case is when root dot data is smaller. So I am 15 and we are looking to delete 25. So then I am saying, I'm making a call to the right side because the data will be on the right side. Hey right subtree, delete 25 out of yourself and return me the root of final right subtree. I will make it my right child. And this else case is once we reach the data. So let's just see it happening. So let's just try to delete 5. So simple, I am saying I am at 25. I am at 35 currently. 35 will say, 35 knows 5 is smaller, so it will be on the left side. So 35 will say, hey left subtree, just delete 5 out of yourself, return me the final root of the tree, I'll make it my left child. This is what 35 is saying. That's what this call is. Correct? I will make it my left child. Root will catch it. After the deletion, whatever left subtree will return as its left child. Now I reach to 20. 20 looks like, oh, 5, we want to delete 5. I am not 5. So hey left subtree, delete 5 out of yourself, return me the root of final tree, I will make it my right child. Now we come to 10. Again we want to delete 5. So 10 will say, hey left subtree, delete 5 out of yourself, return me the root of final tree, I will make it my left child. Now I reached 5. I want to delete 5. What can I do to delete 5? Simple, I will return null. Because if I return null, what is actually happening? What was the call 10 made? 10 made that hey left subtree, delete the element 5 and return me the root of the final tree. I'll make it my left child. So if 5 returns null, 10 will catch null in the left child and 5 will automatically get deleted. Make sense? Now what 10 will do? What was the call 20 made to 10? So 20 simply said, hey left subtree, delete 5 out of yourself, return me the root of the final tree. So root is still same 10, only instead of 5 null is attached here, and so on and so forth. So this is how 5 will get deleted. So let's quickly complete the code. So simple, this is the case, this was just making the calls for left and right side. This else part is when I reach the data. So I'm deleting a guy, I'm deleting a leaf guy. Okay, there are three cases. First, we are discussing the case when we are deleting a leaf guy. For example, 5 or 30. I'll show you for 30 also. When 0 child, when 0 children. Basically, I'm talking about a leaf guy. So how will you define it? Simple. If root dot left double equals to null and root dot right double equals to null, double equals to null. In this case, I'm a leaf guy. I have to simply return null. Okay, easy peasy. Now let's just see the same for k equal to 30. So I am at 35. 35 will say, okay, you want to delete 30. Hey, left subtree, delete 30 out of yourself and return me the root of final tree. I will make it my left child. Now you reach to 20. 20 sees, okay, 35, you want to delete 30, which is greater than me. So 20 will say, hey, right subtree, delete 30 out of yourself, return me the root of that tree. I'll make it my right child. Now you reach to 30. Simply what you are doing here, you simply return null. Who was waiting for it? What was the call of 20? 20 said, hey, right subtree, delete 30 out of yourself, return me the root of the tree. I'll make it my right child. Since 30 returned null, null got attached to it. 20 returned himself only. So 35's left is 20, and here I have a null. That is how 5 and 30 will get deleted. Hope it makes sense. So these two are done. This will work. Okay. Now coming to case 2. What is actually case 2? Case 2 is when you want to delete something which has one child. For example, 10 and 41. So let's just say you want to delete 10. 10 is having one child. Now here you cannot return null. If you return null when you are at 10, in 20 is left, you will get null. But where will the 5 go? Or let's just say you want to delete k equal to 41. If you delete this guy directly, what will happen to rest of the tree? So since it has only one child, what will we do? If I delete 41, 51 will take its place. If I delete 10, this 5 will take its place. So it's pretty simple, right? If the node that we are deleting has only one child, the one child will replace that guy. Okay, so again, how the calls will be made? We want to delete, let's just say k equal to 10. So how k equal to 10 will happen? 35 will say, hey, left subtree, since 10 is smaller than it, 10 is 100% on the left side, delete 10 from yourself, return me the root of that after deletion. I will make it my left child. Now you reach to 20. 20 says, okay, 10, you are 10, so you are smaller than me. Hey, left subtree, delete 10 out of yourself, return me the root of that final tree. I will make it my left child. Now I reach to 10. 10 says, okay, I am the guy that has to be deleted, but I have only one child. So what to do? 10 here at this node at 10, you will return your single child. So what will happen? Instead of this 10, this 5 will be returned and 20 will catch it in its left child. 35 will catch 20. If not clear, maybe you'll get it in this example. So let's just try to delete 41. Although 41 is pretty simple, but let it be. So 35 will say, we want to delete 41, which is larger than me. So hey, right subtree, delete 41 out of yourself, return me the root of the final tree. I'll make it my right child. Now you reach to 41. You cannot delete 41 directly, because then what will happen? If you simply return null, 35 dot right will become null. Then what will happen to this part? But since 41 has only one child, what 41 will say, instead of returning null, let's return my only child. So 41 will return its only child and 35 will catch it. So 35's right will become 51. Okay, that's how the deletion will happen. So if you want to see, maybe this is how it will look like. If I want to present it, maybe I can copy paste. Copy. Then let's add a new page. So this is how the deletion of 41 will happen. When we reach 41, 41 will return its only child. So this thing will get removed and this whole part will get attached here. So you can see it's still a BST. Okay, the BST property has to be maintained. I mean, you cannot change that if you're deleting in a BST. So this is how the tree will look like. Again, 35 is greater is 51, left side all smaller, right side all greater. So this case is also easy when you have one child. So let's just quickly write it up. So we already checked if the node has no child. Now how will we check if it has a single child? So simple, I will say if root dot left is equal to null, I'm 100% sure if I'm reaching this if that both the things are not null. If both the things are not null and left side is null, then 100% right child is the only child that the node have. So simple, I'll return root dot right. Maybe we can write all of them in else if. Else if root dot right double equals to null, simply return root dot left. I'm 100% sure that both the children are not null and left child is not null, so 100% right child is null. So in that case, you return the left child. Now comes the most tricky case, the final case, which is, you can guess, when a node has two children. Not this one, 51. When you want to delete 51. So let's just see how the deletion of 51 will happen. So first of all, you have to analyze it from the diagram. What will happen with the deletion? So if you want to delete 51, okay, we want to delete 51, what should come at its place? If 51 is not here, what do we want to be in the place of 51? If you move this right tree, where will the left tree go? And if you move this left tree, I mean, you want to delete 51. If instead of this 51, you put this right tree here, where will this left tree go? If instead of this 51, you move this left tree, where will the right tree go? So there are many ways to that, but there is one very simple way that I want to discuss. So let's just say I want to delete 51. Okay, I will not do the direct deletion. Instead, what we will discuss, what we can replace 51 with. I mean, I want some value here to which everything on the left is smaller and everything on the right is greater. So what can be here? Can I put 48 here? Let's just say I remove this 48 and I make it 48. So is this still a BST? Is everything on the left smaller? Everything on the right greater? So everything on the left smaller. Oh, instead of 48, maybe I'll give you another example. Instead of 48, let's pick 45 first. So if I remove this 45 and put it here, is everything on the left smaller? Obviously no. Everything on the right greater? Yes, this is there. But everything on the left is not smaller. So 45 cannot be here. Now maybe you can try to guess what can I take from the left side, delete it and put it here. So I think you might have guessed 48. So you can delete this 48 and put 48 here. Why? Because 48 is largest child of the left side. So 100%, since it's largest, everything on the left is smaller. If I'm picking the largest node of left subtree of this 51's left subtree, 100% everything else will be smaller on the left side. And since it was on the left, everything on the right side would be larger. So 48 is my guy. Apart from 48, what else you can think of? So we can pick minimum from the right side also. So I could have picked 55 also, because if I pick 55, again, what will happen? Everything on the left will be smaller because this is coming out of right side. And since I'm picking smallest of right side, everything else on the right would be larger. So I can replace my 51 with anything like 48 and 55. So it's totally your call. You want to choose maximum of left side or minimum of right side. Okay, let's write some code. So simple. First of all, let's get maximum from the left side. Int v is equal to max function. You can write max of root dot left. Then what? You make your root dot data is equal to v. So what I have done till now, I'm saying I picked the maximum of left hand side. So I picked 48. I replaced it with 48. This is what I have done till now. Okay, I wanted to delete 51. Now what I can do, but still there are two 48s, right? And there can't be two 48s. So what to do? In the left side I have to delete 48, and haven't we written it recursively? So what will I say? What you have to understand, I'm still at this place. I'm saying I'm calling delete function on my left side. And what do I have to delete this time? V value, the maximum value that I replaced my current node with. And where do I have to catch it? In current roots left. And in the end, what do we have to do? We have to return root. Make sense? So this is what we have done. Hope it makes sense to all of you. Simply what you have done, you picked the the maximum out of left side, replaced yourself with that, and called delete function on this part. So only 148 can be found now, which will come along this side. And since this will happen on recursively, eventually 48 will get deleted, right? So hope it makes sense. Now coming to time complexity, you can remove this empty page. So first you are searching for the element. Let's discuss one by one for all the three cases. When there were 0 children, 100% I am just reaching till the leaf, and that is order of h. Every time I'm skipping one height, right? When I'm deleting 0 children guy, I'm reaching till the height. I mean, worst I can go till the height of the tree, because every time I search for an element, I either go to left side or right side, so I skip a level. So in this case, it is coming out to be order of h. Now, when somebody has one child, even when somebody has one child, it can happen that one child guy is here, so it's height -1. Worst we can go is height -1, because here we don't do anything. We just reach that element, and after reaching we return whatever is on whichever child the single guy has, left child or right child. Okay, so almost order of h. Now you might have doubt in the third case. So in the third case, first thing that you do is you reach to the element. Okay, so the element can be up to height -2 level or height -1 level. So order of h you will take to reach that element. Then to calculate max, you will take another order of h one time. So order of h plus order of h, because this will get called only one time, this max. Then you are calling delete on that part. So basically what you have to understand, first you reach till 51. Okay, then you got the maximum out of here. Okay, now this although will not be order of h, calculating maximum of a BST is order of h operation, right? So order of h on this side. So for searching the element, you can take maximum order of h, and let's just say you some 3 units of height you took here to reach the element. Once you're deleting the element, again the worst you can go is up to h -3. Simple. Let's understand it this way. Let's just say the node I had to delete, which had 2 children, this is where I found it. Okay, at some x height. Now from the remaining this much part, from this remaining y height, first I found the maximum. Okay, so x plus y, then what? Then I'm calling delete in this part, which will again take maximum order of y. So x plus y, almost order of h, because x plus y is h. X plus y is nothing but height of the tree, and this y is what? Something lesser than h. So overall this is order of h. Hope it makes sense to all of you. So time we will take is order of h. Thank you so much. Hope you enjoyed. See you in the next video. Hello everyone. Today I am back with another beautiful question on binary search tree. So the question is, construct a BBST using sorted array. So first of all, what is a BBST? We know what a BST is, but what actually is BBST? So it stands for balanced binary search tree. So what is a balanced binary search tree? First of all, it should be a BST, right? So for every node, all the nodes on left side, left subtree should be smaller, all the nodes on the right subtree should be greater. And then what is a balanced BBST? So apart from being a BST, for every node difference between left subtree height and right subtree height should be less than or equal to 1, or maybe we can talk about mod of it. Mod of left subtree height comma right subtree height should be less than equal to 1. Okay, so let's just see what this is. So for this node, what is its left subtree height minus right subtree height? This is nothing but 0, because left subtree height is 0. I mean, no left subtree, right subtree, right? 0 0 0 minus 0 is 0. For this node, left subtree height is 1, right subtree height is 0, right? So difference is what? 1. For this node, left subtree height is 2, right subtree height is 2. So the difference between left subtree height and right subtree height is nothing but 0. Here I am measuring the height in terms of number of nodes. Okay, so for this one, left subtree height is 2 nodes. For this one, right subtree height is 2 nodes. Now similarly for 6 and 7 also, the difference between left subtree height and right subtree height is respectively 1 and 0. So for no node, the difference between left subtree height and right subtree height is greater than 1. It's always less than equal to 1. So this is a BST, balanced binary search tree. Now let's talk about this one. Let's check for all the nodes. So for this node, left subtree height, right subtree height difference is 0. For this one, left subtree height is 1, right subtree height is 0. So difference is what? 1. Now let's talk about the next node. This node, left subtree height is 2, right subtree height is 0. So difference is what? 2. It means what? This is not a BST. I mean, I don't need to check any further. If any single node violates the property, at that moment itself we can say this is not a balanced binary search tree. Not a balanced binary search tree. So hope this is clear. What is a balanced binary search tree? Now the question is, we are given a sorted array. We have to create a balanced binary search tree. So the first idea that comes to our mind is, why not call insertion? I mean, I already have made a video on how to do insertion in a BST. So we can call insertions for all the things one by one. So first I have 5, inserted 5 in a BST. So this is how my BST looks like. Now 10 comes. Now for this 5, 10 should come to the right side. So that's how I attach 10. Then 15 comes. 15 will come where? 15 is greater than 5, so will come to the right. 15 is greater than 10, so will come to the right. So 15 comes here. Now comes 20. 20 is greater than 5, so we'll go on to right subtree. 20 is greater than 10, so we'll go to right subtree. 20 is greater than 15, so we'll go to right subtree. This way, this is how 25 and 30 will also come. The same will happen for 25 and 30. So they will also come here. 25 comes here, and then 30 comes here, right everyone? Now you can see this is a BST but not a balanced binary search tree, right? So this tree is skewed, hence not a BBST. I mean, I obviously you can see it visually. I don't need to actually calculate, but if you want, just in case you want, this is not following the property of BBST. Right subtree height is 2, left subtree height is 0, so difference is -2. After taking mod, it's 2, but what it should be less than equal to 1. The same will happen for 15, 10 and 5. So this idea 1 fails actually, which is the most obvious idea that comes to our mind. Now let's talk about idea 2. Now friends, I have this array. I want to make the tree balanced. I mean, the difference of height should be less than equal to 1. So basically it can be 1 or 0. So what do you think? I mean, basically what I want this tree to be as balanced as possible. That's what the concept of BBST is. So what do you think out of all these nodes, all these array values should be the root value? I'm 100% sure by now you have guessed it should be the middle element, 20, right? So what I will do, I will make 20 as my root, and for left subtree, I will pass my left half of the array, and for right subtree, I will pass my right half of the array. I mean, here I chose the middle element as 20. You could have chosen it as 15 because there are even elements, so 2 mid elements. Now what we have done is, this middle element we have selected as root. All the elements on the left hand side, we are saying you form the left subtree. All the elements on the right side, we are saying you form the right subtree. Now, out of these array elements, if I have to form a tree here, what do you think again should be the root? 10 should be root, and the left part of it should go to left subtree, right part of it should go to right subtree. So this is how it will look like. 20, 10 will come here to the left side. I will be left with 5 only. To the right side, I'll be left with 15 only. Similarly here, I have to choose one element. Let's just say we choose 25. Okay, or here what did we did? In case of two mid elements, we choose the second middle. So let's just choose 30. So we choose 30 to be root of the right subtree, and whatever is on the left side of it will go to left subtree. So this is how it will look like, 30, and on the left side I'll be left with 25. Since here I have only these single elements, they will form the corresponding nodes 5, 15 and 25, and you can see this is a balanced binary search tree. Okay, you can check the height of any node, height difference of any node. So hope it makes sense, and logically it makes sense also. Code will be pretty simple, but one thing you have to understand is, when I decided that initially my array is from 0 to 1 to 0, 1, 2, 3, 4, 5. Initially my array was from 0 to 5. Now this middle element was selected as root. Now for the left side, I want for left subtree, I want these array elements to be used. Now I won't create a new array, right? What do we do in these cases? We pass a start and an end, which represents the current array area that we can use. So this start to end will initially contains 0 to n minus 1. Always we will choose the middle element, and mid is equal to start plus end by 2. Then for middle element, I'll create root. Node root is equal to new node with the array element, array of mid. And then what? I will call recursively for left subtree and right subtree. By diagram, you can see that it's going to be recursive code. So for left hand side, I made the call that I pass the array, and left subtree will contain what array elements from start to mid minus 1, because middle is the one we choose right now for the current node. So start to mid minus 1. Now this is how left subtree is created. I have to attach it to my left child, right? So root dot left will be equal to this. And similarly, root dot right will be equal to create right subtree. Right subtree will be in the array from mid plus 1 to the end, and in the end we'll return root. Correct? Now what should be the base case? So let's just analyze for this one. Initially I had array 0 to 5. Okay, let's do it. Let's do it code by code. Initially I had this array from 0 to 5. So we chose the mid element. Mid is what? 0 plus 5 by 2. So 0 plus 5 by 2 will give me what? 2. So second index element will make it as a root element. So 15 will become my root element. This time we are choosing what? I mean, the example I gave you there, I was choosing the second middle element. Here we are choosing the first middle element. Anything is fine. For left subtree, the array will be passed from 0 to 1 index. For right subtree, the array that will be passed is what? 3 to 5 index. Now let's just see, when we are here, when we have to create a balanced binary search tree from this part. Again, start is 0 and end is 1 here in this particular call. So we again choose the middle element, 0 plus 1 divided by 2, which will give us 0. So 0th element will be the middle element, and then we'll make a call for the left and call for the right. So this element 10 will become the middle element. For the left side, the call that will be made is start to mid minus 1. Currently when we were here, what was start? Our start was 0, end was 1, mid came out to be 0. Then 0th element is not 10, it's 5. We made it as the root, Now we made call for the left side. The left side, what did we pass? Start to mid -1. So 0 to, what do we pass? 0 to mid -1 is -1. And for right, what did we pass? For right, we made the call for mid +1 to end. Mid +1 is 1 to 1. So here a node will get created. We don't want any node to be created here. So base case is pretty simple. That is, if start is greater than end, in this case we can return null simply. That's how the code will be. Now coming to time complexity, friends, what do you think? It's pretty easy to guess. All the array elements, for them, I mean, we will have a particular function call in which that particular node will get created. So total order of n functions will be there. Time complexity is order of n. Space will be what? Order of h. Because what is happening? At one time, this much thing will be in the function stack. Then this 5 will get removed and this much will come to the function stack. So space complexity will be what? Nothing but order of h. And here order of h will be log of n because tree is equally divided. Okay. So hope it makes sense to all of you. Thank you so much. Hello, hi everyone. I'm Aman back with another beautiful problem on binary trees. So the question is, we are given a source node. We have to calculate how many nodes are there at a distance k below that node. Okay, so this time we are not given the root node, we are given the source node, and we have to tell from this source node how many nodes are there at distance k. For example, if k value is 4, how many nodes are there at distance k below this one? So 1, 2, 3, 4, this node, and the other node. Distance is calculated by edges, so these two nodes are in fact y2. I think we have more than two. 1, 2, 3, 4, this is 1, 1, 2, 3, 4, this is 1, then 1, 2, 3, 4. So this one, we have 3 nodes at distance k below our node. This is what we have to figure out, and again we are given that corresponding node. So what do we do? From this source node, I want to calculate how many nodes are there at, let's just say, k equal to 4 distance. So I will ask my left child, hey left child, tell me how many nodes do you have at a distance 3 away from you, 3 below from you, left and right node. Now this node will ask its children, hey both of my children, although it has only one child, tell me how many nodes do you have at a distance k equal to 2 distance away. This one will ask its children, how many nodes do you have at a distance 1 away, and this will ask its children, how many nodes do you have at a distance 0 away. Now when this node is asked how many nodes it has at a distance 0 away below this one, so it means what? We are talking about this node. So this node will do what? This node will return 1, this node will also return 1. This node was asked how many nodes it contains below it at a distance 1 away. Left child said 1, right child said 1, so it will return what? 1 plus 1, 2. This k equal to 2 will return what? 3. I mean, you can understand it this way also. This k equal to 2 must have also asked its right child, hey right child, which is null, how many nodes do you have at a distance k away? Since the node was null, that node returns 0. And this will return 2, the same 2. This will return the same 2. Again, correct? This said you are talking about me, so it will return 1, it will return 1, this will return 2, this will return the same value, this will return the same value. Now when asked, now when we were here, we were calculating how many nodes does this node contains below this one at a distance 3. It will ask this its children, so we'll get for this node at k equal to 2, for this node at k equal to 1. When it will ask its children, they will we will see there is no child, so they will return 0, 0. So this will return 0. Now coming to this node, this will be asked how many child do you have at a distance k equal to 1 away below you. This will be asked how many nodes do you have at a distance k equal to 0 below you. K equal to 0 means what? This node will say, okay, you're talking about me, so I'll also return 1. So we'll return 1. This will also return back 1. This node will say, okay, I was asked how many child do I have at a distance k equal to 2 below me. Left child said 0, right child said 1. So I'll return overall 1. This node will also return 1. Now this node asked what? Hey left child, tell me how many nodes do we have at a distance k equal to 3 below you. And the same to the right child. Left child said 2, right child said 1. So this will return what? 2 plus 1. 3. So we have these 3 nodes. Coming to code part, code is going to be relatively very easy. The same thing. I will ask my left child, hey left child, tell me how many nodes do you have below you at a distance k minus 1. Hey right child, tell me how many nodes do you have below you at a distance k minus 1. And I'll return L plus R. When if k becomes 0, it means what? I am at a valid node and you're talking about me, so I should return 1. I mean, when I am here and you're at k equal to 0, you should return 1. Although there should be a base case before that, that if node is null, s double equals to null, we have to do what? We have to return 0. So, I mean, when you reach a null node, you return 0. If you don't reach a null node and distance is 0, it means you're talking about yourself, so you'll return 1. Hope it clears to all of you. Now coming to time, this source could be anything including root. So in the worst case, you need to travel the whole tree. So time complexity will come out to be order of n. While talking about space, I mean, at one time, these many functions, or when let's talk about this s, this was the source. These many functions were there on the stack. Now once this was removed, this was added on the stack. I mean, this function called this one, which called this one, which called this one, which called this one. Once this got removed, this function got added. The same we do in any pre-order, in order, or post order. So space will come out to be order of h. So we have another variation of this question in which we calculate how many nodes do we have from a given node at a distance k away. I mean, here we calculated only the nodes which are below at a distance 4. There we'll calculate what? How many nodes do we have from this node at a distance 4 away, and it could be from it could be in any direction. So 1 2 3 4, this node will also be counted. 1 2 3 4, this node will also be counted. 1 2 3. Okay, this side we don't have anything, so we'll do that question after this one, but this is a prerequisite for that question. So hope you got it, and thank you so much. Hello everyone, I am Aman, back with another beautiful question on binary trees. So the question for today is, we are given a binary tree, we have to find its node to root path. Okay, so I'll explain the question later on, because before that we need to do one other question. Okay, so let's just do this question very quick. You already know this if you are watching this video. If you have reached at this level of tree, 100% you know this question. So the question is, let's first do that question. Given a binary tree which contains all unique values, search if there exists a D in a binary tree. Or D, or let's just say K sounds better. So let's just search for a value K. I want to know simply if there are K equal to 6 or a particular K value exists or not in a binary tree. So this is a binary tree given to me. So let's just quickly start searching. So I mean, you can do any kind of traversal in order, pre-order, post order, right? You basically understand how you're going to do that. You'll just traverse over the tree and check if 6 exists or not. So let me just give a quick dry run to you how it will happen. So we are at the root. Root will ask, root will check if I am equal to 6, currently the value that we are looking for. No, then it will ask its left subtree and then right subtree. Okay, then 7 is not equal to 6, so 7 will also ask its left subtree and right subtree. Now we reach 9 is not equal to 6, so it will ask its left subtree and right subtree. So we reach to 12, we reach to 19. 12 will ask its left subtree, right subtree, both of them will return false. 12 is also not equal to that, so 12 will overall return false. Now 9 asked its left subtree, it got a false. From right subtree also it will get a false, so it will also return a false. Now 9 is not equal to 6. Left subtree is saying I don't contain 6. Right subtree is also saying the same. So 9 will also return false. Now coming to 7. 7 is not equal to 6. And in its children, it doesn't have a 6. So it will also return false. Now we reach to 3. 3 got false from its left side. But 3 will check from its right side also. So we reach to 4 then. 4 will say, okay, I'm not equal to data. But let me check with my left and right subtree. Now we use this 14 said, okay, I'm not equal to data, let me check with my left and right subtree. So you understand, first left call happens. So let me show you it properly. First from 14, first we'll go to left subtree and then we go to the right subtree. So we reached 15 said, okay, I'm not equal to data, let me check with my children. Both the children are null, so it will return false. Children will return false to them. 15 will overall return false. 15 return false. Now coming to this 14 14 got a false from its left subtree. Now 14 will ask its right subtree. We reach the right subtree. 12 said, okay, I'm not equal to data. Let me ask my children. So once we reach here at 6, 6 will say, yes, I am equal to the data that you're looking for. So what do? 6 will return what? 6 will return true. Now minus 12 asked its left child and right child. From left child it got a false, from right child it got a true. So it means in right subtree the data exists, so it will return overall true. Now similarly 14 asked left and right child, from right side it got a true, so it will return the true. Now coming to 4, 4 got a true from left side, so it won't make the call to the right side, right? This is the way in order happens. We first, or pre-order happens. We are doing pre-order here actually, because we are checking with ourselves, then we call for the left and right. So 4 was not equal to data. Left side it got true, so it will return true. It don't need to check on the other side. Now 3 will say, okay, right child is saying that it contains the data. It means, yeah, the data exists, and this is how the calls will happen. If I have to write the code bool check, I'm given node root, and let's just say int d, and then what? Simple. First thing is, if you reach any node, you will check if you are equal to data. So if return root.data double equals to d, you return true. Otherwise you make call to your left or right side, so you recursively call check function for your left subtree root.left comma d, or check root.right comma d. If any of them return true, it means I can return true. Hope it makes sense to all of you, and if nothing this sort of happens, overall will return false. So this is how the code will be, and base case is simple. When 12 asks its left and right child and they are null, so they should return false. So if root double equals to null, they return false. So now we know how to check whether a particular value exists in the tree or not, correct? In a binary tree. In BST, checking is even faster. You can skip one child left or right. You can skip one half of the part, right? Every time. Now let's come to the actual question. So the actual question is called node to root path. Let me copy the tree and a k value. So you are given this tree and you are given a value k equal to 6. You have to give node to root path. This is node 6. You have to give this path. Maybe you have to return this in a list. So this is what you're supposed to return: 6 minus 12, 14, 4 and 3. If k value is given as 9, then you will return 973. It's not compulsory that you will find the data at leaf, right? Or it can happen you never find the data. So how are you going to do that? The way I'll simply explain for 6 and you can get it. So friends, if you notice carefully, you just have to notice it very carefully, okay? Let me remove some extra things, then you can, I think you will be able to view it more properly. I want to return this particular set. I want to return these set of nodes. What unique property do you feel they have right now? I mean, is there something different from other nodes that they possess right now? Yes, if you look carefully, they all are those nodes which are returning true. Yes or no? These all the nodes which are returning true when I was looking for k equal to 6. So what do we have to do now? Simple. I just have to store the element whenever a node is returning true. That's all. I mean, this minus 12 was returning true, so I'll add it to my list. This 19 was returning false, so I won't add it to my list. So let me just copy paste the code and I'll do a quick dry run for you. So let's just write the code. The same code I will use. Let's just say I create a list of node, because I want to store all the nodes. List of node is equal to path. And then what? Simple. If root.data double equals to d, it means this particular node is returning true, so I should store it. So path dot add this particular root node, and then here also when I was returning true, I should add this node, path dot add root. What if I tell you this is it? You have done it actually. Maybe you're not very clear with the code, but this is it actually. So let's just see how it will happen one more time. So let me clear out everything, and I'll do it in a very quick manner because I'm very sure you will understand it very easily now. So this is my list initially completely empty. Now I am at 3. 3 is not equal to data, so it will ask its left child and its right child. Left child first, first we will come back from the left subtree, then I will go to the right. So we are at 7. 7 is not equal to data, so it will ask its left subtree. 9 will ask its left and right subtree. All of these guys are returning false, 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 and this 7 also returned false, so none of them I added in the tree. Now let's see the other side. We reach to 4. 4 said I am not equal to data, but let me check with my children. So first left call will happen, and this whole subtree, once we come back out of this tree, then we make call to the right child, right? This is how recursion works. So we reach to the 15. 15 checked with its children. 15 also returned false. Now we are at 14. 14 called its children, minus 12, and minus 12 called 6. 6 said okay, I am equal to data, so I am returning true. This is what point in your code if root dot data is double equals to d. So what you're doing, you're adding it to your path. So you added 6, and then you did what? You returned true. So this 6 returned true. Now I'm at minus 12. What did you do at minus 12? When you were at minus 12, you said I'm not equal to data. Check, let me check with my left and right child, and then if any of them returns true, it means I can say yes, I have the data. There is data is within me somewhere. This call is represented how? Here, this when your root value is minus 12, that's how you can get it. You check with your left child, you check with your right child. In this case, what would have happened? Right call must have returned true. So that is why we want to add this guy also. Now when we are at minus 12, simple. What would have happened? When we are at minus 12, we are basically representing this particular part, that root value is minus 12. Root says okay, I am not equal to data. I called for my left and right side. My right side returned true. That is why the 12 was supposed to return true. Since 12 is supposed to return true, before that 12 will also get added in the list. So 12 is also added. Now let's see it one more time. When you reach to this 14, when you were this 14, you were not equal to data, but you called for your left and right side. Left side returned false, but right side returned true. So what do? You were also going to return true, this 14, and before that we will store you up. This is how it will happen, so on and so forth. Hope it makes sense. Now coming to time complexity, in the worst case we can traverse the whole tree. So time complexity is order of n. Coming to space, now one time what can happen at max? First these many functions will be there in the stack. Now once this 12 gets removed, these all functions will be there on the stack, right? So at max, order of h function, whatever is the height of the tree, that many functions can be there in the stack. Hope it makes sense to all of you. Thank you so much. See you in the next video. Hello friends, I am Aman, back with another beautiful problem on binary trees. LCA, lowest common ancestor. So let's just quickly see what LCA is, and then we'll have some discussion. LCA is defined between two nodes P and Q as the lowest node in tree, which is an ancestor to both P and Q. So maybe let's just try to understand it by an example. This is very easy. So let's just say I want to get, let's just first talk what ancestor means. Can I say this B is an ancestor of D? Yes. This A is an ancestor of D? Yes. For these nodes E and H, A is an ancestor to both of them, right? B is an ancestor to both of them? Yes. C is an ancestor to both of them? Yes. Is D also an ancestor to both of them? No, right? So lowest common ancestor is, out of all the possible ancestors, the last ancestor at which the division happens. After which there is no more any common ancestor. So let's just try to understand it by some examples. So LCA of M comma H. LCA of M comma H. So all the common ancestors are these A, B, and C. Last common ancestor is what? C. Now let's see for other examples. LCA of J comma L. So for J and L, I think if I'm not wrong, these are all the ancestors, right? A, B, C, D are all the ancestors, while the lowest common ancestor is nothing but D. Now let's talk about the last example that we have, LC of D comma C. So for D and C, so for C, all these are ancestors. For D, all these are ancestors. What is the last common ancestor? C. I mean, that's how it's defined in the question. It's C. Cool. So when something is in the path, this thing, I mean, when they are in the same path, the upper thing will be called ancestor. As I said, that's how they have defined it in the question. Although it's arguable that you can say maybe B. Okay, because C, how can C be an ancestor row itself? So that's a different thing. But the way it's defined in question is that for both of them, the ancestor is C. Lowest common ancestor between them is C. So the way it is defined in the question, the lowest common ancestor between them is between D and C is C. Okay. Now how we are going to do that? So in the previous question, in the previous video, in the previous problem, I have made a video on get node to root path. Okay. So let's just see. Let's just try to do it here. Get node to root path for M. This is the node to root path. It will contain what? It will contain M, F, D, C, B, and A. Let's try to get node to root path for H. This is what I get. I get what? H, G, C, B, A. Now friends, you can see A is a common ancestor to both of them. B is common ancestor. C is the last common ancestor among both of them. Hence C is the answer. Cool. Let's try to do it for J and L. So node to root path for J is for J it is J E D C B A. J E D C B A. For L it is, where is L? L M F D C B A. L M F D C B A. Correct everyone? So A is a common ancestor, B is a common ancestor, C is a common ancestor, D is the last common ancestor, hence D. And let's do the same for D and C. So lowest common ancestor. The node to root path for D is DCBA. And for C it is CBA. So the last common ancestor, A is a common ancestor, B is a common ancestor, C is a common ancestor. Last common ancestor or lowest common ancestor is nothing but C. Hope it makes sense. Now this node to root path function I have already explained in a previous video. You can 100% watch that out. I'm not going to explain that here. So let's just code it up. So I have two lists. I want to get the lowest common ancestor between P and Q. So I got the path, the common, the node to root path for both of them. What do I have to do? Simple. Let's create two variables. Int I is equal to L1 dot size minus 1. J is equal to L2 dot size minus 1. Now let's create a variable previous match. So basically what I'm planning to do is I'll keep two variables, one I here and J here. Okay, they are matching, move ahead. I here, J here, matching. I here, J here, matching. I here, J here, they're not matching, so the previous match was answer. That's how I'm going to do that. That is why I'm keeping the variable previous match. So I'm start putting two pointers in the end of both of them. Now while I is greater than equal to 0 and J is also greater than equal to 0, simple. If in the L1 ith guy is not equal to L2's jth guy, it means what? I have to return previous match, whatever previous match was there. Else it's pretty simple, they are matching, do I minus minus, J minus minus, and update previous match equal to, or first let's update previous match and then do I minus minus, J minus minus. Previous match is equal to nothing but L1 of I. Okay, now this is done, this is done, while loop is done. So the way it will work is again simple. I have a I variable, I have a J variable, they are matching, update previous match, go ahead, they are matching, they are matching, they are matching. Here I and J will not match, so what I'll do, I'll return the previous match. So answer should be return previous match. There will be some edge cases. Let's just see those edge cases also. So what are the edge cases? Let's just say I have to get lowest common ancestor for these two pi's. So in this case, what will happen? I have, for E, I have EDCBA, and for C, I will have CBA. My I variable will be here initially. J is here, match. I is here, J is here, match. I is here, J is here, match. Now then, I and 0, J will become -1. So in case J becomes -1, what is the answer? Again, if when J becomes -1, answer is still the previous match, right? So that is why till the time J is greater than or equal to 0, we are running. And as soon as J becomes negative, still the previous match is answer. The other way around is possible. Now let's just see one more. If both the nodes are passed as E, or let's just say both the nodes are passed as C, in that case what will happen? CBA, CBA. So I is here, J is here, match. I is here, J is here, match. I is here, J is here, match. Now the loop breaks. Both of them have become -1. Even in this case, the previous match is my answer. So I can return previous match. No edge case. Just wanted to show you. So hope it makes sense to all of you and you understood this. Now, friends, we can improvise even this for a BST, okay? That I will do in a different question. But the LCA for BST can be calculated in a more easier way, because there we have some BST properties also with us. Thank you so much. See you in the next video. Hello everyone, I am Aman, back with another beautiful problem on BST. So problem name is recover binary search tree. We are given a BST. Again, what is the property of BST? For every node, all the nodes on the left subtree will be smaller, all the nodes on the right subtree will be greater. This property is true for all the nodes. Now, what they have done in the question, they have chosen any two random nodes and they have swapped their values. So let's just say this is a BST that I have in front of me. What they have done, they have, let's just say they randomly chose these two nodes and this is what they have done, swapped them. Now I have to identify these two nodes. Okay, so this is what is given to us as an input and we have to figure out these two nodes. Now the problem is very simple, to be very honest. What do we know? We know in order of a binary search tree sorted. So if, let's just say, if this is what is given to us as an input. If, let's just say, instead of this I would have got the original BST, then this is its in order, correct? Now what they have done, they have actually swapped the two values. So instead of this, how I will get in order is, I'll get the in order in this format. I'll get 9 here and I'll get 14 here. Now I have to identify these two nodes, correct? Now, very easy. It's not that hard to imagine. Simple. The question is actually nothing but we are given an array, sorted array, in which two values are swapped. You have to identify those two values. Now, how hard it is to find these two values? So simple. Let's just take let's just understand it case by case basis. Let's just say if this was an sorted array initially. So that's how its curve should have been. I mean, every index is greater than the previous index and smaller than the next index, right? Now they have randomly chosen two value. Let's just say second index and fourth index, and they have swapped them out. So this is how my sorted array looks right now. I mean, this is the best way to understand. If I do it via values, you won't understand nothing. Now I'll try to do the same. So I will start with the first index. I will check, am I greater than the previous guy? Yes, I'm greater than the previous guy. It means nothing is problematic here. This time at index 2, am I greater than the previous guy? Yes. So nothing is problematic here. Now this place, am I greater than the previous guy? Obviously not. I'm not greater than the previous guy. At this point, array of I is less than array of I minus 1, which simply means what? This is a problematic place. Now in this problematic place, you can see in diagram, out of array and I and array of I minus 1, which is the problematic element? So in this case, we can clearly see array of what? I am at the third index, right? This second index is the problematic element. So first time this occurs, when first time this occurs, simple. First element is first, or may I call it problem one. Problem one is array of I. Now let's go ahead at this place. Current element is again, now at third index I was not greater than the previous guy. At fourth index also I'm not greater than the previous guy. So second time this issue occur. Now when this time this issue occurs among these two elements 4 and 3, which is the problematic one? Obviously this element is the problematic one, right? I mean, let me highlight the problematic ones here also. These are the problematic ones. So first time when I was at third index this issue happened, so we said I am at I minus 1th guy is the problematic one. When I reached here at this index, again this problem occurred that I'm not greater than the previous guy. So this time array of I is the problematic one. So second time this issue happens, second time this happens, so we can get problem 2, but this time problem 2 is array of I. Now let's try to understand it by an example what we did just now. So I'll keep on traveling. Array of I is greater than array of I minus 1, array of I still greater than, array of I still greater than array of I minus 1. This time I'm not greater than the previous guy. When I'm not greater than the previous guy and first time this is happening, who is the problematic element? The current element. Oh sorry, in this case it is array of I minus 1, right? When first time this issue happened here, when I was not greater than the previous guy, array of I minus 1 was the problematic one. So who is the problematic one? 14 is the problematic one. So first issue I identified. Now let's go ahead. I'm still greater than the previous guy. This time I'm not greater than the previous guy. So second time this issue happened. When second time this happens, who is the problematic guy? The current element. So that's how I'm able to identify both the elements. Now when this is clear, there is one more edge case to that. The case 2 is when they swap two adjacent elements. So let's just say they swap these two elements. So you can see the swapping here. Now this time what will happen? Here I am greater than the previous guy, here I am greater than the previous guy, here I am greater than the previous guy, here I am not greater than the previous guy. So first time issue happened. When first time issue happens, what we say? First element is array of I minus 1. But what will happen? This issue is never going to repeat again, right? It will never happen again. I mean, here it happened that I am not greater than the previous guy. So we said first element is array of I minus 1, which is true. But again, it will not happen. I am greater than the previous guy here also. So what will you do when first time the issue occurs? You will say that I don't know if two adjacent elements are swapped or two distant elements are swapped. So first time this issue occurs when I am here, I am not greater than my previous guy. So simple I will say first issue is array of I minus 1, second issue is array of I. Now, if I find the second issue anywhere else, I will update the second element. That's how I'm going to do it. So let's just see it by an example. So this was, let's just say in order of a sorted in order of a BST which is sorted, let's just swap two adjacent elements. So let's go. I'm greater than the previous guy, I'm greater than the previous guy, I'm greater than the previous guy, still greater than the previous guy. This time I'm not greater than the previous guy, and this issue is coming for the first time. Since this issue is coming for the first time, I will say my problem 1 is nothing but array of I minus 1, which is 13, and my problem 2 is what? The current element 10. Now if I find the issue again, I will update my problem number 2. So if I go ahead, I'm greater than the previous guy, greater. So I never found the problem again. If I would have found the problem again, I would have updated problem 2. So this is how I handle both the cases. Now to apply this approach, what you will do, you will create the in order array out of this BST. We can save creating this in order array. Okay, why? Because when we traverse a BST in order, I mean, to apply this approach, what do I need? I just always need to compare myself with the previous element. When I do in order of a BST, actually I am traversing the BST in a sorted format. So I always have the previous access. I will maintain a global previous, and that's how I'm going to do it. Let's just see it here. So initially my previous is null. Okay, and let's just start traversing. So I reach this 3. 3 is the first element from which I am coming back from the left. Left side is null. So I will make myself as the previous. First of all, let's just say we reach 3. First element that will reach in order is 3. Now I will compare myself with the previous guy. Previous guy is null. So I cannot compare myself. I'm the 0th index. Okay. And now before going ahead, let's update myself from as the previous for the next guy. Now we go ahead. I reached 5. I am at 5. Am I greater than my previous element? Yes, I have the previous element now in the previous variable. Am I greater than? So there is no problem. Now before going ahead, I'll update the previous to 5. Now let's go ahead. The next in order element that you will find is 7. You reach 7. Are you greater than the previous guy? Yes. So let's update the previous and let's go ahead. Now I reached 14. Am I greater than the previous guy? Yes, I am greater than the previous guy. So there is no problem here. Let's update myself. Now let's go ahead to the next place. I reach the next place 10. Am I greater than the previous guy? No, I'm not greater than the previous guy. And the issue is coming for the first time. So first time this issue occurs and I'm not greater than the previous guy. So we say what? First element is the previous element and second element is the current element. So I know what? Problem 1 is 14. I update problem 2 as 10. Correct? Now let's go ahead and update previous to 10. Now I go ahead. Next element I found is 13. I'm greater than 3, so not a problem. Next element I found is 9. Am I? And previously we will update the previous also, right? When we were going from 13 to 9, we'll update the previous also. Now here I reached out to 9. Am I greater than the previous guy? No, I am not. So this issue is coming for the second time. Now when second time issue occurs, who is the problematic element? The current element is the problematic element, and I will update my problem 2 as 9. So this way now I will never find a problem again, because after 9 I will update previous as 9, and for further elements I will always find I am greater than the previous guy. And I am able to maintain the case also when two consecutive elements are swapped, because first time the issue occurs I update both problem 1 and problem 2. If second time issue occurs, I update problem 2 again. So let's just quickly code it up. So I've created problem 1, problem 2 and previous. Initially all these three are null. Simple. And what do I have to do? I have to do in order traversal. So simply when I am at 10, I want the previous, or let's just say it here, when I am at 5, I want the previous to be storing 3. So first I have to come back from left, right? So first I will make the left call, helper root dot left. Then what? Simple. Now this is the situation that somebody has reached out from the left. So for example, if I'm at 10, my left call has been completed. Now my previous is storing this guy 14. So I want to compare myself with it, right? Whether I'm greater than the previous guy or not. But previous is initially null and I don't want this comparison to happen for the first guy. Correct? So you will say if previous is not equal to null, because if previous is null, it means you are at the first node. There you don't want any comparison. And I am greater than the previous guy. It simply means what? There is a problem. Now, if the problem is coming for the first time, this problem 1 variable would be null. So if problem 1 is double equals to null, it means problem is coming for the first time. Let's update problem 1 and problem 2. So when first time issue occurs, what have we planned? When first time issue occurs, we will update problem 1 as the previous element and problem 2 as the current element. So simple. Let's just compare this with previous dot value. Now I'll simply say problem 1 is equal to previous guy and problem 2 is equal to current guy. Now if again it happened that I am smaller than the previous guy, but problem 1 is not null, it means the problem is occurring for the second time, because first time it's already been updated. So in this case I will simply update my problem 2 only. So problem 2 will become what? The current root element, and that's how it will end. At the end, now I have completed myself. Now I'm going to go to the right side. So before going to the right side, what do you have to do? You have to update previous with yourself and then call the right side. I mean, this is what you want, right? What we want, that from 10, when I'm going to the right side, the first element that I'll reach is 9. For them, previous should be me. So that will be all for this problem. And the base case would be there. Base case is obviously if root is null. and return. In that case, we don't want to do anything. So now I have both the problems or both the elements, both the nodes stored in my problem1 and problem2 variable. Time complexity is, since I'm traversing over the whole tree, it's order of n. Space is just the recursive stack space, which happens via in order. I mean, if you look at the code, this all is constant operation, right? This is all constant operation. So what are you doing? You're just simply doing in order. So we know the time and space for that. Time complexity in that case is order of n, and space complexity is order of h. So that will be all for this problem. Thank you so much, everyone. Hope you understood everything. Bye bye. See you. Hello everyone, I'm Aman back with another beautiful problem on trees. So the question is maximum sum path starting from root. We have to calculate maximum sum path that starts with root. For example, in this tree, this is this one. Sum will be 14 plus 8, 22, 22 plus 6, 28, 28 minus 2, 26. This is the maximum sum path that starts with root. You can try all other paths. It's not necessary that you reach to the leaf. I mean, I could have stopped here. For example, if I try to calculate, I mean, let's just say if this would not have been here, then I would have calculated this 14 plus 6 plus 5. Okay. Now let's see here. If I start from this side, this I think I'll get is this one, 9 plus 4, which is 13. The only constraint is I have to start with the root. Now let's see here. If I start here at 9, I should go till here, and the sum that I'll get is 10. So the answer in this case is what, 10. If I start exactly here, the maximum sum path starting at this root is nothing but this minus 3, because if I even include one node or any node, any other path, I will get even smaller sum. So the answer in this case would be nothing but minus 3. Hope the question is clear to you. Now let's just see how am I going to solve them. I want to calculate maximum sum path starting with the root. Okay, what if I know maximum sum path starting with this point and maximum sum path starting with this point? Then I can make the decision whether I want to include this side or even none of them. So let's just start. I'll ask the same to everyone. I will ask 10. Hey, tell me maximum 10. Tell me maximum sum path starting from yourself. It will say nothing but 10. If I ask the same to 7, 7 will say nothing but 7. Now I want to know here maximum sum path starting with this 6. This 6 asked left tree said starting with me maximum is 7. So, and right side I have nothing. So I will include this and I'll get 6 plus 7, 13. Now maximum sum path starting with this minus 8. Left subtree said that from this point onwards, the maximum sum that you can get is 10. Right tree said maximum sum starting from this point you get is 13. So I will 100% include this one and I get 13 plus minus 8, which is 5. Now let's ask the right subtree. This will return maximum sum path starting with itself as 5. This will return 1. Now at this point, maximum sum path starting from this point, this will say what? Left subtree is giving me 1. So maximum you can start from this is minus 6 plus 1, which is minus 5. Now maximum sum path starting with this. Left subtree says maximum sum path starting with me is 5. Starting with this point is minus 5. So 100% minus 3 will include the left side and it will become 2. And 4 asks the same to left subtree. This side said maximum sum path starting with this point is 5. Starting with this point is 2. So 100% it will include the left tree and it will become 9. Hope it's clear. Now let's just see it on another example. So let's just say for this one, maximum sum path starting from this place would be nothing but minus 4. Maximum sum path starting from this place would be nothing but minus 3. Now let's see the turn of minus 2. Minus 2 says maximum sum path starting with left tree, it's 0. Starting with right tree, right subtree is minus 3. So why would I include this right side to myself? I would rather be alone, right? So this minus 2 will return nothing but minus 2. Now let's start for this minus 3. Maximum sum path starting from this place is minus 4. Starting from this place is minus 2. So why would minus 3 include anyone? It will remain alone and it will return minus 3. Hope it makes sense to all of you. Now maybe we can see it here. Maximum sum path starting from this place is what? Minus 5. From this minus 1 is minus 1, minus 3 is minus 3. Now when I start with this minus 2, maximum sum path starting with the left side is minus 1. Starting with the right side is minus 3. So why would we include negative parts? I will start exactly from here. So maximum sum path starting with minus 2 is minus 2. Now for this 4, right subtree it has nothing. Left subtree it got minus 5. So why will it include left side? And it will simply return 4. Now when I come to 9, left side is saying maximum sum path starting from me. Whatever it is, I don't care. That is -2. This side, it is 4. So we'll get what? We'll choose this side and we'll get 9 plus 4, 13. Hope this is clear to all of you. Now let's just quickly code it up. Maximum sum path starting with root. So I'm simply saying, hey left tree, tell me the maximum sum path starting with yourself. So this I'll call root dot left. The same I'll ask to my right side. Int r is equal to maximum sum path root starting from the right side. It is root dot right. Now for me, I will 100% include myself because we are talking about maximum sum path starting with this point. But for a node, if left side is negative, right side is negative, do we want to include that? 100% not. When both are positive, I want to include what? I want to include the larger of them. So this we can write simply as maximum of left side sum, right side sum, and 0. If both of them are negative, we are not including anyone. We are returning from ourselves. If one of them are positive and negative, so I'll choose the positive one. If both of them are positive, I'll choose the higher one. And base case will be if root is null, simply return. Now coming to time complexity, since we are traversing the whole tree, time complexity will be nothing but order of n. While coming to space complexity, these many functions will be there at max on the stack, or height number of functions. Similar to, I mean, what we are doing exactly, we are doing nothing different from post order, right? Go left side, go right side, and then do yourself, doing some work at yourself. So space is order of h. Now this is not the actual question. Let's just come to the actual question. Actual question is, we have to calculate maximum sum path passing between any two nodes. Okay, through any two nodes. For example, in this tree, maximum sum path between any two nodes is this much. Oh, let me draw it again. This much. This will come out to be 5 plus 6, 11. 11 plus 14, 25. 25 plus this is what? 8, 6, 14. 14 minus 2, 12. So 7 and 3, 37. This side, I'll get answer as 37. Now, for this side, the maximum sum path, the maximum path between any two nodes will be this much only. Will be this much only. This is the maximum sum possible between any two nodes, which comes out to be 15. Now, here maximum sum between any two nodes, this will come out to be this much. Right? 50 plus 60, 70, 80. So answer in this case is 80. Hope the question is clear to all of you. Now, how to solve this? So this solution is highly dependent upon the previous problem. Let's go through the previous code one more time, where we were calculating maximum sum path starting from this root element. Okay. What was the previous problem that we solved? Maximum sum path starting from every node. This is what we were calculating. So maximum sum path starting from this place that we will get is 10. Here I'll get 7. Here I'll get 5. Here I'll get 1. Now maximum sum path starting from this place, 7 plus 6, 13. I'm just again doing the previous question, not this one, because this will help me, the previous question will help me solve the current problem. Now here, maximum sum path starting from this node, this is what? Minus 8. It has two options, it will choose this one, so it will return 5. Now here, this will return minus 6 plus 1, minus 5. The maximum sum starting with this is minus 3. Maximum sum starting with this is what? Minus 3 plus 5, which is nothing but 2. And maximum sum starting from this place will be what? Minus 40 plus, it will choose this 5, minus 35. This is what we have calculated. Now we want to actually calculate maximum sum path between any two nodes. Now friends, my claim is, whatever the maximum sum path is between any two nodes, it will pass through one of the node. I mean, beat this, it will always pass through one node. Whatever is the maximum sum path in a tree, let's just say this is the tree, it will 100% pass through some node, right? Even if it is this much only, still it will have one root. Whatever is the maximum sum path, it will have a root. So I will do what? I will give every node the chance to be root, and I will calculate maximum sum path there. For example, what is the maximum sum path between any two nodes starting from this, where it acts as a root? Nothing but 10. Maximum sum path between any two nodes in which this is root. So maximum sum from the left side is 10, right side is 13. So maximum sum path passing through this will be what? passing through this node will be what? 10 plus 13 plus minus 8, which will come out to be what? 23, and 23 minus 8 will be what? 15. So maximum sum path between any two nodes passing through this is 15. No better sum is possible which will pass through this. Similarly, maximum sum path passing through this, just passing through this. For that, what do I need? Left side maximum sum, right side maximum sum. I have left side maximum sum 7, right side maximum sum is 0. So maximum sum path in which this node is acting as root is nothing but 13. Maximum sum path, let's calculate here, for between any two nodes in which this will act as root will be what? This left side maximum sum, right side sum plus this. So left side sum is 5, right side sum is negative, so we won't include it, correct? In this case, so 5 plus 3, which gives us minus 2. So maximum, plus 2. Maximum sum path in which between any two nodes in which this is acting as root is 2. Now, maximum sum path passing between any two nodes in which this node is acting as root. So left side maximum sum is what? 5. Right side maximum sum is what? 2. So maximum sum path between any two nodes passing through this will be what? 5 plus 2, 7 minus 35. So I just have to get maximum of all these, which I can do via global variable. Let's just see one more example. Let's just do here. Let's first calculate maximum sum path starting from every node. So starting from every node, this will be minus 10. This will be 10. This will be 50. Starting from this, 20 plus 50, 70. Starting from this is what? Minus 20 plus 70, 50. Maximum sum path passing through this root. Now, to calculate maximum sum path between any two nodes, the maximum sum path will 100% pass through a root element. So let's just treat everything as the root. This from this element, when this element is root and you want to calculate maximum sum path in which this is root, what do you need? Left side sum, right side sum, and your current node. Left side maximum sum is 10, right side maximum sum is 50. So maximum sum path between any two nodes in which this will act as root will be what? 10 plus 50, 60 plus 2, 80. Similarly, maximum sum path between any two nodes in which this minus 20 is acting as a root is what? Left side maximum is minus 10, right side maximum is 70. So maximum sum path between any two nodes passing through this will be what? This minus 20. We won't choose the left side since it's negative, plus 70, which is 50. So maximum sum path between any two nodes passing through this will be what? 50, that you can see. This is that. So hope this is clear to you. So basically, simple. Let me put it one more time. Whatever is the maximum sum path, it will pass through some node that will act as a root between the maximum sum path. We are giving every node the chance to be root of that maximum sum path. We are getting the maximum left sum, maximum right sum. If both of them are positive, we will include that and our sum will become something like this. If maximum sum path, if left side sum starting from this is negative, right side sum starting from this is positive, then maximum sum path passing through this node will be this much. And if both of them are negative, maximum sum path starting from this is negative, starting from this is negative, we'll choose just ourselves. So simply we are going to use our previous code. I will call this previous code and behind the scenes I will get what I want. Oh, I think it's already there. Maybe let's just remove this and paste it again. It will help me. I have a global variable. Answer is minus infinity. Basically, I'm calculating answer at every place, maximum sum path between any two nodes. And I call this via my global function. At the end, I'll return answer. Now here, currently I'm calculating maximum sum path passing through every node. So for maximum sum path pass when this current node is acting as root, I can calculate it because all the data that I need is here. So simply, well, let's put a p variable. P is equal to max of left comma 0 plus max of right comma 0 plus root dot data, and then answer will be max of answer comma p. So these two additional lines, just make sure that every node where you're returning maximum sum path starting from this place, starting from this root, you're also calculating maximum sum path where this will act as a root node because you have the left sum, you have the right sum. So you're also calculating the maximum sum path between any two nodes at this particular node. Hope it makes sense to all of you. Thank you so much and see you in the next video. Hello everyone, I am Aman and back with another beautiful question on trees is find lowest common ancestor of a binary search tree. We have already learned, I have already made a video on how to find lowest common ancestor of a normal binary tree. That method is already applicable here, but we can do something better in BST. So I'll start discussing it directly with with the new method that works only for BST. So first of all, what is lowest common ancestor? Lowest common ancestor is defined between two nodes P and Q as the lowest node in tree, which is an ancestor to both P and Q. So lowest node, which is ancestor to both P and Q. Let's just say my P node is 7 and Q node is 14. So I want to find the lowest common ancestor between 7 and 14. So if you see the lowest node, which is ancestor to both of them, is 10. So their LCA is what? 10. Let's just try some other example. Let's just try to find LCA of P is equal to 14 and Q is equal to P is equal to, let's just say instead of 14, let me choose 7 and Q is equal to 3. So I have to find the LCA of both of them. Now if you see 10 is an ancestor to both of them. 5 is also an ancestor to both of them, right? But among 10 and 5, 5 is the lower one. So LCA, the lowest common ancestor to both of them is what? The node 5. Now let's just try for, let's just say we are given P is equal to 7 and Q is equal to 9. Let's just try to find LCA in this case. So in this case, the ancestor to both of them are 10, 5. And as per the definition of LCA, we count 9 also as the ancestor of 9. Okay. So in this case, the lowest common ancestor for both of them is what? It is 9 only. Hope the question is clear to you. Now, again, there are different ways to do that. Some of them are directly applicable in a binary tree that I've already explained in the previous video. You can watch that out. In this video, we will discuss only about how we can do it optimally for a BST. I mean, what changes for a BST. So as we know, for a BST, for every node, all the nodes on the left side, on the left subtree are smaller. All the nodes on the right subtree are greater. Okay. So let's just say I try to find lowest common ancestor for 7 and 3. This is what I have to find, 7 and 3. So what I'll do, I'll simply start with my root. I will check where is 7 and 3. Are they both on my left side, on my right side, or in the different directions? So if I see, I will find what? That 7 and 3 both are smaller. So they will be 100% on my left side. So I'll reach to my left. Now I reach this place. What will I see? That one of the values is smaller than me and the other is greater than me. It means this is the point where we are going to diverge. Correct? This is the point. This current node is the point where we are going to diverge. So 100%, this is the LCA. That's how we calculate it. Now, let's see it one more time. Let's just say we are interested in calculating LCA of 14 and maybe I can create a node here. Let's just say I create a node what? 11 here. Now let's try to find the LCA, lowest common ancestor, in a BST for 11 and 14. So I start with 10. What do I see? Both the values are greater than me. So 100% they are on my right side. Now I reach to 15. Now what do I see? Both the values that I'm looking for, 11 and 14, are smaller than me. So 100% they are on my left side. I reach this left place. Now at this point, what do I see? One value is smaller and one value is greater. So 100% this is the point of diversification, and hence this 13 is the lowest common ancestor. Make sense? So that's how it will be. Let's write code for only this part. Then we will see the scenario in which one of the node is LCA of both of them. So let's quickly see. I'm given the node P and Q. I'm given the root node. So what will I do? Simple. If root dot value is less than P and root dot value is less than Q, or let's just say P dot value and Q dot value. So this means what? I am 15 and the LCA that I'm looking for, the nodes for which LCA we are calculating are 20 and something like 25. So I'm smaller than both of them. So 100% both the nodes are on my right side and I'm not the LCA. So we'll go to right side. Simply we'll make a call on the right side and we'll say, hey, right side, return me the lowest common ancestor for both of them. Root dot right, comma P, comma Q. Similarly, if the root is greater than both of them, is greater than p dot val, and then root dot value is greater than q dot val, it means what? The current root data is greater than both of them, so 100% both the data elements are smaller than me and they should be on the left side, so we'll go to the left side. So I'm saying, hey left subtree, return me the LCA of both of them, root dot left comma p comma q. And else means what? That I'm sitting at a point where one of the data node is on the left side, other node is on the right side, right? I am greater than one of them and smaller than one of them, so at this point I am the LCA, so we'll simply return root. And obviously the base case, which if you want, if you can write, otherwise you don't need to, because you will always be given valid nodes and you will never make the fake call. But let's just write it to be on the safe side. If root double equals to null, return null. Now let's just see how do we cater the scenario when we are looking for the LCA of 7 and 9. So we reach to 10, we find what? Both the values are smaller, so 100% I'm not the LCA. Let's go to the left side. I will ask my left subtree to tell me LCA. Now I reach to 5, I see 10 and 9, both the values are greater, so 100% LCA is on the other side. Now I reach here, what do I see? If you check the conditions, what will happen? None of these conditions will become true. What are these conditions? That both the data value are smaller than me. Are both the data values smaller than me? Obviously not, one of them is equal. Are both the data values that I'm looking for greater than me? 100% they are not greater. So in this case, what do? We simply return the root element, and this is what we'll do, we'll return 9. So hence this code will work for all the cases. Now coming to time complexity, every time you're skipping a level, you are either going to the left child or right child, so time complexity becomes order of h. Coming to space also, this 10 will call 5, and I mean every time I'm skipping a height, so in my recursive function, recursive stack space, I can have only order of h number of functions, so space is also order of h. Hope you got it. Thank you so much. See you in the next video.